Okay, thank you for the introduction, and first of all I would like to thank the organizer for giving me the opportunity to give a plenary lecture here, and especially to Professor Abbasi, and it is always a great honor to collaborate with him. For me, it's the second time here in Fez, and I really enjoy the place. And please let me give the outline of the topic. So first of all, I will give some general things about what a magnetic curve is, and then I will provide some results about contact magnetic curves and some periodicity of magnetic curves, and finally homogeneity of magnetic trajectory in SL2R, but also in other spaces. So what is a magnetic curve? So it starts from no problem from physics. So a classical description in Euclidean space. We have a static magnetic field, so it is a vector field with zero divergence, and we have this Lorentz force. E is the charge, D is the velocity, M is the mass, should be here, and the Newton equation writes like this. Okay, so when we approach to the speed light and we have another law of motion, Lorentz force, and it is described like this. Okay. Anyway, we do have this property. We see here that because of this and the energy, this quantity is orthogonal to P, and this implies that both the speed and the energy are constant, and if we assume that V is stationary, that means it's time independent. Okay, so in general, what is the Lorentz force? Is the acceleration equals something applied to the velocity vector. We'll see what that something, that capital phi is. So if we go back to the Euclidean 3 space, so if we have the magnetic, so this vector with zero divergence, we associate trivially the two form, and the divergence free means the closeness of two form. So this gives an idea how to move this problem from practical problem from physics to a Riemannian manifold. So what do we have here? So we start with a Riemannian manifold, and we say that the magnetic field is defined by a closed form, and by using musical isomorphism, we lift the first index of F, and to define the Lorentz force, so that capital phi, which is an endomorphism of the tangent spaces. Okay, so now we have also the Lorentz force, and we are able now to write the Lorentz equation in an arbitrary Riemannian manifold. So we have this this background, the Riemannian manifold, and the closed form defines a magnetic field, and we say that gamma is a magnetic curve of this background, so this dynamical system associated with F, if satisfies this equation. So we see the analogy with geodesics. If in the absence of magnetic field, so when F is 0, the previous equation is nothing but the equation of geodesics. both magnetic curves and geodesics are characterized as critical points of the energy action, and magnetic curves modify the energy action, so they provide from a variational principle. I don't want to say too many details now. The existence and uniqueness of geodesic remains true for magnetic curves, and also because of the skew symmetry of the Lorentz force, we have that magnetic curves are constant speed and hence constant energy, exactly as in the original problem from physics. And this, in the case when is arc length parametrized, the magnetic curve will be called the normal. So these are some analogies between geodesics and magnetic curves. Probably the first difference is that balance property of geodesics is no longer true in the case of magnetic curves. Okay, some examples. For example, if M is a surface, we consider the area element. So any other two form is proportional to the area element. So it is a function times this sigma. F is called the strength, and of course is closed, the dimension is 2, and if Q is constant, F it is called uniform, geometrically it is parallel, and so F is, this Q is a real number. A curve with constant velocity V is a magnetic curve if and only if the curvature is Q divided by V. So I'd like to quote this from Barros and the others, a group from Sevilla and Granada. The geometric partner of the Landau-Hall problem, so the original problem on surfaces for uniform magnetic fields, is nothing but the computation of the curve with constant curvature. Okay, so what happens in some examples in the Euclidean plane? We have circles, so magnetic curves that are not geodesics. Okay, so circle with some radius, 1 over strength. The small circles with this radius, but in the hyperbolic plane we have either closed curves that are circles, but also non-closed closed. For example, in the upper half plane, there are horocycles. Okay, so they are not close. At a certain point, we ask the problem of periodicity of magnetic curves. In dimension 3, the situation is very interesting because we recover the initial problem from E3. So two forms and vector fields may be identified via the volume form and Horsar operator, and magnetic field means divergence-free vector fields. Okay, so special class of divergence-free vector fields are killing vector fields, and will provide the notion of killing magnetic fields and killing magnetic curves. Okay, so in the same dimension 3, we have a naturally defined cross product by the volume form. Okay, so we have a nice way to construct to write the Lorentz force and the Lorentz equation, because if V is a killing vector, we define the corresponding magnetic field like this. So using the volume form and put V here. Okay, and the Lorentz force is this one, and we have to solve this this equation. Okay, so the Lorentz equation can be written in a nice way, and which is a second order differential equation, and we'd like to have some explicit solution of this equation. Okay, so let me give some results we had in the last few years. So in Euclidean 3 space. Okay, so the natural vector field, or the easiest one, is a constant one, and if we compute the magnetic curves, so it depends on the initial velocity. If it is parallel with the field, it is a line. If it is orthogonal to the field, it is a circle. And in case it is oblique, it is a helix. Okay, so these are notions known from physics. But I never seen what happens with other killing vector fields, with the rotational killing vector field. So we tried to solve this, and we succeeded. This it is a work with Simona Brut, and we did some other in S2 cross R in the sphere. You will see in a minute why we choose. So except these three, the dimensional three, we will see what happened in other dimension, and we see why the dimension 3 is important for our case. Okay, so my talk will be focused on this, the last three, as well as on this one. Okay, so here there are other references, and okay, so all these manifold where we study magnetic curves are Sasakian, because Sasakian manifolds are, on one hand, the odd-dimensional version of Keller manifolds. For Keller manifold, I have the pleasure to say that several studies on Keller magnetic curves are done by Professor Adachi. He is here, and we studied the counterpart of Keller manifolds and Keller magnetic curves. And let me briefly recall what is a Sasakian manifold. So it is a 2m plus 1 dimensional manifold. So we have a phi psi eta structure. Phi is a 1-1 tensor field, psi is a vector field, eta is a one form, satisfying these relations. They are not all independent, but they are all these four conditions are very useful in computations. Okay, and we have also a compatible metric, G. M is said to have an almost contact metric structure if these conditions are satisfied, and M is called almost contact metric manifolds. Consequently, psi is unitary, and eta and psi are dual. We define a two-form, so a fundamental two-form here, and if omega is d eta, we have the notion of contact metric manifold. Okay, and the Sasakian manifold is a normal contact metric manifold. Contact is here, normal is characterized by the normality condition vanishes, it is a tensor who must vanish, but we have this tensorial characterization of Sasakian manifold among almost contact metric manifolds. So this is an equation who gives a covariant derivative of phi, and as a consequence we have also this one. Okay, so because of this condition, this omega is a good candidate for a magnetic field. In fact, we have more. It is an exact two form here, and in our formulation, this eta is called potential one form. Okay, so let me briefly recall the notion of Fresnel curve of osculating order R. So we have T is a tangent vector, and we have the orthonormal frame of so nu1, nu R minus 1 satisfying this one, where K1, Kr minus 1 are positive functions, so they are called curvatures. Okay, so if this happens, we say that R is osculating order R for the curve gamma. Examples: geodesics, circles, K1 is constant and K2 is 0, so the other do not exist, and helices, where the first two curvatures are constant and the third curvature is 0. Okay. These are important because of for us. Okay, as I said, omega is a good candidate to have a magnetic field. So we multiply q by omega by a constant here. So let Fq be a magnetic field. We will call it contact magnetic field in analogy with Keller to form. And the magnetic field there is Q times the Keller to form. Okay, if Q is 0, of course, magnetic field is absent, so it's not interesting for us. So we assume Q is different from 0, and the Lorentz force phi Q is precisely Q times that 1/1 tensor field in the definition of the second manifold. And we have some results here. So a classification of magnetic curves in Sasakian manifolds of arbitrary dimension. So we have geodesics, but not because of the vanishing of Q, but as an integral curve of the Reeb vector field psi. Some non-geodesic phi circles with this curvature and with a constant contact angle. The contact angle is the angle between the tangent vector to the curve and the Reeb vector field applied at that point. Legendre phi curves. So Legendre curve is curves orthogonal to the Reeb vector field. So they belong to the contact distribution eta. Again, with constant curvature, so they are helices with K2 is 1, and the more general is phi helices of osculating order 3 with axis psi and with these curvatures, where this theta is a constant contact angle. So all these magnetic curves in Sasakian manifold are slant curves, so that contact angle is constant. Okay, so this order 3 inspired us to see what happens when we are working with the Sasakian space form. So first, remember, let me recall the definition of a geomotetic transformation of the Sasakian structure here. So if we have phi psi eta g, we modify this structure in this manner. So where alpha is a constant, a positive constant, and we have a Sasakian space form is a Sasakian manifold whose phi sectional curvature is constant, And if we make a de-homothetic transformation of a Sasakian space form, we still obtain a Sasakian space form, and these are how the curvature changes. Okay, so this alpha will be used in a little bit later. Okay, so remember that the typical models for Sasakian space forms are non-standard spheres when C is greater than -3. So that we will call Berger spheres, including here also the unit sphere, the Heisenberg space of phi-sectional curvature -3, and B2n cross R, where B is a complex space form, and here is the metric is not so there is a construction there, is not the product metric. Okay. Okay. So what happens in Sasakian space form? So first, remember this classical result. If we have the unit sphere endowed with a canonical Sasakian structure, and if we apply a de-homothetic deformation, the curvature is 4 over alpha -3, that alpha in the de-homothetic transformation. And conversely, if we have a Sasakian space form of constant sectional curvature greater than -3, it is isomorphic to S 2m plus 1 equipped with a de-homothetic deformed Sasakian structure. Okay, so the result is the following. Let gamma be a normal magnetic curve, so it is parametrized by arc length in the sphere corresponding to the contact magnetic field phi FQ. Then gamma is a normal magnetic curve on a three-dimensional unit sphere embedded as a Sasakian totally geodesic submanifold in S2m plus 1. So in the case of sphere, the study of magnetic curve for arbitrary dimension reduces to dimension 3. Okay, so in the table, remember our studies, the fragment dimension is 3. Okay, so this happened also in other Sasakian space. So we have for the Heisenberg group, so R2m plus 1 of -3. We have this one. So we have helices, and we are able to see the reduction for the codimension of the curve. So instead of working in R2m plus 1, we are working in dimension 3, and this Heisenberg dimension 3 is totally geodesic, and the totally geodesic, and the Sasakian structure of Heisenberg of dimension 3 is that induced from the ambient. Okay, and in this case, we have again the least, and the important is the last one. We have again the reduction theorem for the codimension, but this is based on the reduction for Keller manifold. So in Keller manifold we have so there are either geodesics and Riemannian circles. Riemannian circles meaning that the first curvature is constant and the second curvature is 0. So it is this one. Okay, so so we can reduce the dimension here to 2. Okay, so from here we studied the product manifold, the magnetic curves in M2 holomorphic sectional curvature K cross R. Okay, they are all, this spaces S2 cross R respectively, H2 cross R are important also from other point of view. Okay, let me, I don't remember which hour I started at 10, I think, 10? Okay. So, let me see what happens in Berger spheres. Okay, so, we are interested in the periodicity of magnetic trajectories in Berger sphere. So we have M3 of C, the non-standard sphere. Okay, so we have this circle bundle. Here is a canonical projection. We remember the model, so we take SU2, G is the algebra, we have the quaternionic base of small SU2s of G, I, J, and K. Using this base, the group SU2 is described by this, and we consider the invariant metric G1 of constant curvature 1 induced from this inner product on the vector space G, and we know that we have this we consider first the two sphere of radius small r in SU2, in those with the previous metric, and the pi became Riemannian submersion if and only if the radius is precisely square root of alpha over 2. This alpha is from the geometric transformation from the sphere, unit sphere to M3. And this C is 4 over alpha minus 3. Okay, so if we consider a curve beta on the base here on S2R, and the complete lift of beta, so the pre-image of the curve is a flat surface in SU2, and it is usually called Hopf tube over beta. When beta is closed, it is called Hopf torus. And if beta is a grid circle, the Hopf torus is minimal in M3. And we prove this. So if gamma is a magnetic curve in M3 of C, the projection curve is a part of a circle on S2 of R. Of geodesic curvature, this one, K and tau are the curvature, and so the first and the second curvature of gamma in M3 of C. And if gamma is periodic, so the projection should be periodic, so it is a circle. And we have the magnetic curve gamma is precisely a geodesic in the Hopf tube of HB. Yes, so P is minus 1 of beta. Okay, so we have also this result. So the set of all periodic magnetic curves of arbitrary strength on Sasakian space form M3 of C can be quantized in the set of rational numbers. What does this mean? So we have a relation depending on rational numbers. So I saw this on Stefano talk. So a kind of rational number appears for the periodicity. So probably is more or less the same idea there. And we have this one. When C is 1, we retrieve a result of a group of people studying magnetic curves in S3, a group of Sevilla, and they obtain this. So they said gamma is gamma on S3 of 1 is periodic if and only if this expression is a rational, this number is rational. So if we particularize, so alpha is 1, r, small r should be 1 over 2. This capital R is the radius of the projection of the circle beta, so it's less than r. So this condition is an extension of this one. Okay. Okay, so let me pass to the last part of my talk. So, magnetic trajectory in SL2R. In fact, I put here only SL2R, but because the paper is published, but we have a result also for Berger spheres and also for the Heisenberg group in dimension 3, and I think I hope to have some time to point out the differences. Okay, so SL2R is the space of two-dimensional matrices of unit determinant. We know the Iwasawa decomposition NAK into the nilpotent part, abelian part, and maximal torus. Okay, so this provides us global coordinates on SL2R. So we have this decomposition, and this mapping is a diffeomorphism onto SL2R from H2 hyperbolic plane of curvature -4 cross S1, and if we take the Lie algebra SL2R, so the set of matrices is zero space, we denote by E, F, and H these matrices. The commutation relations are this one. The Lie algebra corresponding to N, A, and K are denoted by this one. NAK from the Iwasawa decomposition. We have this one, so this vector will be important for our study. So we have this decomposition, and we take the left invariant vector field. So we take the invariant frame U1. Just to fix the notation, these are very known things. So U1, E2, E3, and on the Lie algebra define the inner product such that these are orthonormal, and by less translating. Okay, so we're left translating this inner product. We obtain a left invariant Riemannian metric is this one. And what do we have here? We have a globally defined contact form, d eta. Eta equals d theta plus dx over 2y, the red vector field defined by E3, and we define the endomorphism phi like this, and we can check that this quartet defines satisfies this relation, meaning that we have a Sasakian structure on SL2R. Okay, so. This Sasakian structure is left invariant. It is known as the canonical Sasakian structure on SL2R, and we take F equals d eta. So we want to study magnetic curves in this framework, and we take a magnetic curve we compute the acceleration, we put these these are left invariant, but they are not orthogonal. Okay, so we have this one. So this E1, E2, E3 defined previously. Okay, and the magnetic equation writes. In fact, we put also the strength Q here. So the magnetic equation, the Lorentz equation, is written like this. Okay, so we have a complicated system of second-order differential equations. The last one confirms that the magnetic curve is a slant curve. Okay, because this is 0, so means eta gamma prime is constant. Eta gamma prime is precisely g of psi and gamma prime. Gamma prime is unitary, psi is unitary, so this means that the cosine theta is constant, so theta is constant. So this confirms the result we already know. And so from now on, to avoid the confusion with the two theta, in LaTeX is a difference, but it's better I change theta to sigma, the contact angle, and there are some tricks to try to solve this system. Okay, so if we remember that, okay, I didn't say, it is arc length parametrized, we have also this relation. So the equation becomes this one, together with the condition of being slant. Okay. Reeb flow, so the integral curve of psi are geodesics, they are magnetic curves, with sigma is 0 or pi, depending on the orientation. Okay, and now we can do something more. So we represent x and y in this way. We put this constant, and everything reduces to this one. So that very complicated system reduces to this one, which can be solved explicitly. So we have solution. But in our this first paper on magnetic trajectory in SL2R, we are interested in periodicity of magnetic trajectory. So we were not interested in other things. Okay, so let me. So the idea is to see what is the relation with the Lie groups here. So remember, let me recall some things. So G is said homogeneous if there exists one parameter subgroup such that gamma is expressed like this. Because in that paper we studied, we gave some examples obtained as one parameter subgroup, and we studied when those curves are magnetic curves. Okay, so we wanted to see that all magnetic curves are in that form. We had a reason for this, but it was not true, but almost true. So remember the notion of homogeneous geodesic. In a Lie group with the invariant metric, Riemannian metric, all geodesics starting that the identity are one parameter subgroup. So this was one of the motivation we believe our initial guess, but was not true. Because of the metric is only left invariant, one parameter subgroup are not necessarily geodesics. So we remember by invariant obstruction U, so defined by this, and the Levi-Civita connection is written like this. On SL2R we define this, and these vectors, these matrices, these vectors are orthonormal, okay? And this known criteria, one parameter subgroup is a geodesic if and only if that obstruction tensor is 0. So the corollary one parameter subgroup xtx in SL2R is a geodesic if and only if either x belongs to span of E plus F H or x is span of E minus F. So E minus F is tangent to the fiber of the projection SL2R to H2 minus 4. And a homogeneous Riemannian manifold M is called a space with homogeneous geodesics or a Riemannian geospace if every geodesic gamma T is an orbit of one parameter subgroup of G. So this notion is introduced by Kowalski and Berger in 1991. And we compute everything for SL2R. So we change a bit, we rotate the span of E and F. So we had E plus F and E minus F to be orthogonal, and we rotate that two vectors, and we have this one. We compute the bivariance obstruction. And we compute also the endomorphism field, and we obtain this result. So if gamma is exponential of Tx, the Lorentz equation holds true if and only if we have these two conditions. So the one parameter subgroup xTx, where x is this one, is a magnetic curve if and only if A minus B equals Q over 2 square root of 2. Okay, so it's something analog to the geodesics. And in case when B is minus A, in order to have non-geodesic magnetic curves with trans Q, we need to ask C is different from 0, otherwise we get geodesic. In this situation, we have a precise expression for A and B. Okay, so it is not, I said that gamma is not of the form xtx, but we still have that every contact magnetic curve in SL2R is homogeneous in the following sense. So it's very related to homogeneous geodesics. So every contact magnetic curve gamma, starting at the origin and with the charge with the trans Q, is a product of the homogeneous geodesic gamma x. So this is a homogeneous geodesic, and the charge vector field flow this one. So it is a product between a homogeneous geodesic and something fixed. Okay, so it is almost okay. So homogeneity in this sense. Okay. Okay, so I will skip this part probably. Let me record also this one. So did you prove this? So using Euler-Arnold equation, so we have okay. So if we take a curve gamma, we set in a group. This is the general setting. We put capital omega gamma to the -1 gamma prime. And the acceleration can be computed in this way, and gamma is a geodesic if and only if this happens. Okay, so we wanted to apply this to our setting, but we do not have geodesic, we have magnetic curves. So we will modify the Arnold equation to what we call magnetized Arnold equation. So remember, if we assume G is semi-simple, we take the semi-Riemannian metric B, normalized killing metric, and we define this capital I called moment of inertia tensor field, and this mu, the angular momentum, so E applied to omega. We compute the derivative of omega, and we have this equation. And the so-called Euler-Arnold equation, sometimes found in the literature Euler-Poincaré equation, is this one. This for geodesics. So, how do we apply to SL2R? So, we take the Lie group SL2R cross SO2 that acts by left invariant SL2R from by right translation from SO2 in this way. So AB applied to X, AX B to the -1, and we compute the this is the diagonal subgroup K cross K, so K is in fact SO2, okay, from Iwasawa decomposition. So we have this, and we prove that it is known. So it can be proved that the natural reductive structure on SL2R. So we have this. We consider the vector space P. We have this decomposition shows that it is reductive. So this in here, and this is in P. And it can be checked that it is this decomposition is naturally reductive with respect to this one. And the Euler-Arnold equation can be obtained in this way. So the killing form is this one, the normalized killing metric is this one. The endomorphism is only the transpose. The Euler-Arnold equation can be written in this way. And we apply directly to SL2R. So we compute omega, where the coefficients are, we previously have seen, this, and this. The moment of inertia I, which maps C1 to -C1, and the other are preserved. The momentum mu is this one, and if we compute the Euler-Arnold equation, we get this one. Again, this equation shows that a slant condition for geodesics. And if we go further, for B and C, we can compute because it is pretty easy, okay, to compute. And we have this expression. So this matrix is exactly the exponential of something here, 4s omega, so the projection to K, okay. So this is precisely what you obtain from the red vector field, okay. So if omega, if we set the initial conditions, omega is completely defined. So what is remain to solve the ODE to find gamma, okay? And we consider this expression for gamma. So we take gamma in this form, and it is a geodesic if and only if u, so the coefficient here, u is 2a, and we make the computation, we obtain this one. Okay? But so this is already known from this one. I prefer to present this because to magnetic curves is just a kind of copy of this, and to do analog computation for with an extra term. So here is a product, but if we think to SL2R cross SO2, it is exactly the orbit of the exponential of Sx, the identity in that big group. Okay, the magnetized Arnold equation is this one, and we do the same thing, and the same thing we obtain. So everything is analog to for the geodesics, and we obtain this one. So here is the expression we previously obtained, and here is charge magnetic trajectory corresponding to psi. Here is no, it's okay. Okay, so here is the geodesic, and here is okay. Only a few words about the other spaces. So maybe this one first. For Berger sphere, so with some changes, we obtained a similar result. Every contact magnetic trajectory is homogeneous. We compute everything on the Berger sphere, and it is a product of homogeneous geodesic and the charge Reeb flow. But for the Heisenberg group, this trick doesn't work, because the generalise of killing form, so this killing form on Niels 3 is 0. So the strategy we adopted is not working here. But we have a very interesting framework, namely the Heisenberg space Niels 3 can be represented as a OSC by U1, where OSC is the oscillator group of dimension 4, and we were able to move first to oscillator group, and then to everything from the magnetic background to oscillator group, and then to move the result back, and we obtained the homogeneity of magnetic trajectories. Okay, thank you for attention.